Thermodynamics. Energy can be in two forms, that is, energy in transition and energy in storage. One is storage and another one is transition. Energy in transition means you will get this transferable energy, that is heat and work. Energy in storage means it is kinetic energy or potential energy, internal energy. Jones, James Prescott Jones, from the year 1843 to 1848, conducted several experiments to establish the quantitative analysis or an equivalence between heat and work. He conducted quantitative analysis. Quantitative analysis or a relationship between heat and work. Out of that, the best experiment is paddle wheel work. He got a better result in the paddle wheel work experiment. Let me write the word experiment. Let me mark as a figure A. In that figure A, a known quantity of fluid is taken, that is in a container or a compartment. Let me write that a rough sketch, which is isolated. There is no transfer of energy and mass between the system and the surroundings. A container which doesn't allow to pass energy as well as mass. Let me write it as isolated. Inside that container, there is inside the container there is a fluid which is considered as a system. Which is considered as a system, and the system, that is fluid, is system by a stirrer, or else you call it as a paddle wheel, or else you can call it as a stirrer. And a thermometer is placed to measure the temperature. A thermometer is placed to measure temperature. When the stirrer is stirred or a work done on the system, when the work done on the system, the fluid gets disturbed and the temperature is increased. Initially, without stirring, if a temperature is T1, then the final temperature is T2 after the stirrer doing work on the fluid. T2 is greater than T1. Now the figure B I will write. The same container I will take. Same container. Which is isolated. There is no transfer of energy and mass between the system and surroundings. Now, surrounding a fluid, let us consider this fluid. As a fluid. which is work done on the system. A stirrer is provided here. Work is done on the system. A thermometer is kept here to measure the temperature. One more thermometer is kept outside that particular system that also measures the temperature. Now, what is there outside that uh, fluid? It is water bath. Surrounding this, it is water bath. This is water bath. When the work is done on the system through the stirrer, when the work is done on the system through a stirrer, temperature increases. Then, when the temperature is increased, this is the conductive material, then heat is transferred from this hot fluid to the water. Initially, the temperature is T1 and it will go to T2. Then, again, it will come back to T1. When it will come back to T1, then this is at higher temperature. Heat will transfer to the water bath, and temperature of the water will increase. Temperature of the water will increase. If I write a PV diagram, if I write a PV diagram, 1 to 2, it is 1 to 2, work is done on the system. Then again it is coming back to its initial state. Then it is rejecting a certain amount of heat. That means Joule found that the amount of heat rejected by the fluid was equal to the increase in energy of water bath, and also it is estimated in terms of rising temperature of the water. So it's very simple. Here, change of state from 1 to 2, the final temperature is T2, where work is done on it. The same fluid, when it is temperature increase, it is surrounded by a water bath. Heat will transfer from that high temperature water to the high temperature fluid to the water bath. That is, heat will reject. And again, this particular fluid will regain its initial uh, state. The court judge concluded that net work done on the system was always proportional to the net heat rejected. Now, let me repeat that PV diagram. PV diagram. Now, during the change of state from 1 to 2, work is done on the system, and it will come back to its initial state by rejecting the heat to the water bath. Then Joule concluded that after conducting lots of experiments, uh, the ratio, that is W is to Q, that is W by Q for a first experiment, and then at the same time we conducted a number of experiments. We got certain ratio, that is 4.189 Newton meters per calorie. This is cyclic process. This is what we can, one more thing we can conclude here. For a cyclic process, the ratio is almost same. From this, the first law of thermodynamics for a system undergoing a cyclic process is defined, and that definition is when a closed system undergoes when a closed system undergoes when a closed system undergoes a cyclic process, a cyclic process, the cyclic integral law, the cyclic integral law, work transfer is equal to cyclic integral law, heat transfer. This is The first law of thermodynamics for a cyclic process. Now, what is mathematically cyclic integral of W is equal to cyclic integral of Q. This is the first law of thermodynamics. Uh, I'll make one more analogy here. It is mathematically, if I write cyclic integral of W is equal to cyclic integral of Q, then what is the difference between these two mathematical expressions? Let me call this as the first and this as the two. Mathematically, both are true, but W, it is high grade energy, and Q, that is low grade energy. The conversion of high grade energy, complete conversion of high grade energy to low grade energy is possible, whereas the complete conversion of low grade energy to high grade energy is not possible. Therefore, mathematically, whenever you are writing the first law of thermodynamics for a cyclic process, you should write like this. The left hand side always write the W, and the right hand side you write Q. Now this is for a cyclic process. Let us consider a non-cyclic process. Before that, let me take this particular problem. A system executes a cyclic process. The first thing should come to your mind is it is cyclic process. Now once the cyclic process comes with the first law of thermodynamics is cyclic integral of W is equal to cyclic integral of Q. That you should go. This is first law of thermodynamics for cyclic process, during which there are four heat transfers. There are four heat transfers. There are Q1, Q2, Q3, Q4. Four heat transfers are there. They have given this for 900 joules, 80 joules, minus 800 joules, and 150 joules. And four work interactions, W1, W2, W3, W4. And W1 is 200, W2 is 150, W3 is 300, and W4, that is unknown, we have to calculate. Find the magnitude and direction of the force. Magnitude means that amount, and direction means whether it is positive or negative. Whenever it comes positive, so look here, the sign convention for work, that is work done on the system is negative, work done by the system is positive. Similarly, if for a sign convention for a heat absorbed, it is positive, heat liberated, it is negative. See, this positive indicates Q here, it is heat supplied or absorbed. Positive, heat supplied or absorbed. Negative, it is heat rejected or liberated. Q4, positive, heat absorbed. Then here, W1, positive, work done by the system. Next, positive, work done by the system. Work done by the system. So since it is a cyclic process, very important, cyclic process, I can apply the cyclic integral of work transfer is equal to cyclic integral of heat transfer. What is the cyclic integral of work transfer? W1 plus W2 plus W3 plus W4 is equal to heat transfer, that is Q1 plus Q2 plus Q3 plus Q4. You know all the data of W, Q1, Q2, Q3, 4, and here only unknown term here it is W4. Whereas in mathematical steps, you will get minus 320 joules. Minus 320 joules. Now the magnitude is the amount of work done on the system. Is 320 joules. Based on the minus, you are telling work done on the system. This for a cyclic process, first law of thermodynamics for a cyclic process. Now, how the first law of thermodynamics for a system undergoing a non-cyclic process. Now, see, I'll write a PV diagram. PV diagram. That's PV. Uh, 1 to 2, then again coming back 2 to 1. This is cyclic process. A single process 1 to 2. This is non-cycle. Initial state is not same as the final state. If I write like one more here, that is 1 is different, 3 is different. Here 1 to 1 initially same as the final state. That is very important here. Now for this cyclic process, we are writing cyclic integral of W is equal to cyclic integral of Q. Now what about individually? Here also 1 to 2 is also non-cyclic, 2 to 1 is non-cyclic if I take individually. Now we are writing for individually, that is non-cyclic process. Now let me consider a system before going to define. Let me consider two systems. Two systems. One I supply a W and another I supply a Q. If one form of energy is W, the output will be another form of energy, that is Q. If input is Q, the other form of energy output will be W. Now the input here, this is W, is equal to output. See, some new thing I will introduce. These two are transferable energies. If work here enters here to the system, that whatever stored energy which is present here, let me call that as a E1, it will change to E2. It will get disturbed and output will be Q. Here also, when Q is entered, initial stored energy, it will be E1. It will go to E2. It will change. If it is not changed, then Q is equal to W and such system doesn't exist, where Q is not equal to W. There something will happen inside the system, that is, it will change the stored energy and as output, the work you will get. And here, if a work is the input, something will happen, that is E1 to E2. Initial stored energy is E1, the final stored energy is E2 after Q is going out. Now then something will change, that is, I will call it as a delta E, a change in stored energy, a change in stored energy, that is delta E. E of W you know that is work, and Q you know that is heat, and delta E is change in internal energy, that is delta E is E2 minus E1. Then W is the work, Q is the heat, delta is the stored energy. Now let me write the sign convention here. Work done on the system, therefore it is minus Q, and heat is liberated, that is sign convention is minus Q and delta E. I'll take this Q to the right hand side, left hand side, then it will become Q minus W is equal to delta E. This was this I got from this first system. Let me take the second system. What is the input? Q, and what is the output? W. Something will change, that is change in stored energy. I'll take this W to the left hand side, then it will become Q minus W. Before that, heat absorbed, it is positive, and heat done work done by the system, that is also positive. After applying the sign convention, take the W to the left hand side. Q minus W is equal to delta E. Whether heat is the input or a work is the input, whether a work is the output or a heat is the output, you get the same expression. That is Q minus W is equal to delta E. This Q minus W is equal to delta E. Now this is your first law of thermodynamics. Q minus W is equal to delta. This is first law of thermodynamics for a non-cyclic process. Now, by other things I can say, the difference in transferable energy. These are transition energy or transferable energy, and this is stored energy. The difference in transferable energy is equal to change in internal energy. And also, we can analysis one more thing, that is delta E is equal to E2 minus E1. When you will tell internal energy, stored energy is increasing, stored energy is increasing. If this difference should be positive, then you will tell increasing. When it is positive, when E2 is greater than E1, then you will tell change in stored energy is increasing. Next, another one is decreasing when E1 is greater than E2. A statement, whenever they will use state first law of thermodynamics, state first law of thermodynamics, then the statement should be in two statements. One statement it is for a cyclic process, and another statement should be for non-cyclic. Both for both process you should explain. Now, for a cyclic process, the cyclic integral of W is equal to cyclic integral of Q. Complete conversion of high grade to low grade energy. And for a non-cyclic process, it is Q minus W is equal to delta E. The difference in transferable energy is equal to change in stored energy. Next topic, it is energy or property of a system. The title will confuse you, telling that energy is a property of the system because we define the two things, that is point function and path function. And when it is a path function, we said that work and heat comes under path function, and point function, that is state variables, that is pressure, volume, and temperature. But you are telling energy or property; these are energy, you are telling it is a property of the system. Don't confuse, we are not telling that here energy, that is work. We are telling here this energy, it is stored energy, is a property of a system. Stored, this energy is stored energy. That is what we said, what we got the notation earlier, it is delta E. Delta E a property of the system. We are not telling here work is a property of the system or Q is a property of a system. Here, which one? Stored energy is a property of the system. We are proving that. Let us consider a PV diagram. Change of state from 1 to 2 by following the path, let me say, by following the path L. And it is going back to its initial state from 2 to 1 uh, by following path M, or else it may follow one more path, that is N. It means a change of state from 1 to 2 by following a path, single path, that is N, and change of state from 2 to 1, it is going to the initial state, that is either it can follow M or N. Now let us derive this. Now consider a system which changes states from state 1 to state 2 by following a path N. Let us consider that. Now let us write in the first law of thermodynamics. Writing first law of thermodynamics. Thermodynamics for the process 1L2. It is 1L2. It is what? 1L2 becomes what? It is a non-cyclic process. Now for a non-cyclic process, you can write Q minus W is equal to delta E. Now it is for a path L. Let me write with a notation that Q belongs to path L and this W belongs to L, and this is delta E L. Let me mark this as equation number 1. Now similarly, I'll write it for 2M1. See, I'll consider this. Now similarly for 2M1, that is also non-cyclic process. That 1L2 is a non-cyclic and 2M1 becomes a non-cyclic. I will write Qm minus Wm is equal to delta E M. That becomes for equation 2. Now this 1L2 and then from 2M1, this comprises a cycle. Therefore, for a cycle 1L2M1, now applying the first law of thermodynamics for a cyclic process, applying the first law of thermodynamics. Now, for a cyclic process, you know that is cyclic integral of work transfer is equal to cyclic integral of heat transfer. See, this is 1L2 is non-cyclic process, therefore we use this. And 2M1 is also a non-cyclic process, that is Q minus W is equal to delta E. Now 1L2M becomes a cyclic process. Now what are the work transfer you get? In 1L2 you get WL, network transfer WL, plus one more work you get WM. Then in the heat transfer you get QL and QM. Let me rearrange the term here, that is QL I keep here as it is, then WL I will take it to here, QL minus WL. This I'll take it to the QM to the right hand side, therefore WM minus QM. Now if I take minus out, this will become QM minus WM is equal to QL minus WM. What is QM minus WM? It is delta EM minus delta EM, and this is QL minus W is delta EM. Now this what we got from a cycle 1LM21. Now similarly for cycle, one more cycle is there, which is that 1L2N1. Similarly for cycle 1L2N1, same expression can be get, that is delta E, but following part N is equal to delta E N. See, if I mark this as a star 1 and this as a star 2, this is for a cycle 1LM1 and this is for a cycle 1L2N1. Now right hand side are equal, therefore I can write minus delta EM is equal to minus delta EN. Minus minus cancel. What is the ultimate conclusion? Delta E, stored energy by following the path M, is equal to stored energy by following the path N. That means stored energy doesn't depend on the path in which it is followed. That is, either it follows M or either it follows N. It doesn't depend on path in which it is followed. Therefore, if it is not depend on path in which it is followed, means therefore it will become point function. Therefore, it will become point function. Then the point function means it is a, if it is a point function means it is a property of the system. This is the proof that stored energy, it is a property of the system. This is very important. Next, different forms of stored energy. The symbol E, whatever we use till now, that E represents, it is for a stored energy. It is for a stored energy. There are two modes in which energy may be stored in a system. That is, one is macroscopic, that stored energy can be in the two forms, that is macroscopic energy mode. Macroscopic energy mode. And another one is microscopic energy mode. In the macroscopic energy mode, we get this kinetic energy, and potential energy. Let me write this kinetic energy as the EK and potential energy as the EK. In microscopic energy, I get here the internal energy. I use notation U. Now this kinetic energy, in this kinetic energy, it is, we know that it is, the definition is, the mathematical expression is half mv square. and potential energy is mgh. And at this stage, internal energy just I will write it is a function of temperature. It depends on temperature. Therefore, the stored energy E becomes it is a summation of macroscopic mode, that is EK, kinetic energy plus potential energy plus internal energy. If we neglect in most of the problems, we are not getting this kinetic energy and potential energy. If we neglect kinetic energy and the potential energy, then EK will be zero, and EP, that is potential energy, will be zero. Then E becomes U. Why I written in stored energy in terms of U? Because most of the problems or most of the derivation from now onwards, we will use Q, that is internal energy. It is a function of temperature. Therefore, first law of thermodynamics, it will become Q minus W is equal to delta U. Q minus W is equal to delta U. Or else you can remember Q minus W is equal to U2 minus U1. So Q, it is in joules, Q in joules, and W also in joules. If this left hand side is in joules, obviously the right hand side also should be in joules. Internal energy, it is also joules. So look at this one. Q also joules, W is also joules, and Q and W are transferable energy, or else those are path functions. But this unit is also joules, but this is a point function, and it is a property of the system. It's a isolated system. An isolated system means there will be no energy transfer, and also there will be no mass transfer. Such system is called as isolated system. If I consider a system, I will write here this symbol indicates the system is isolated. There will be no transfer of energy and mass between the system and surroundings. If I apply a first law of thermodynamics, that is Q minus W is equal to delta U, or else Q minus W is equal to U2 minus U1. There will be no energy transfer. Therefore, Q is 0, W both are energy, path functions. This is 0. That is, change in internal energy, it is 0. But take U1 to the left hand side, that is U1 minus U2. One more thing we can conclude is two things we can conclude, that is the change in internal energy is 0. Change in internal energy is 0. Or else internal energy remains constant. Internal energy remains constant. This is analogy for an isolated system. Perpetual motion machine of a first kind, that is PMM1, perpetual motion machine of one, PMM1. The first law of thermodynamics that states, the general principle of the first law of thermodynamics is conservation of energy. Conservation of energy. What is that conservation of energy? Energy is neither be created nor be destroyed. Neither be created nor be destroyed. This is the basic principle or general principle for a first law of thermodynamics. And what is energy is neither be created nor be destroyed, but it gets transferred from one form to the another, and it can be observed here in the system. Work is transferred and Q it is transferred. Work is one form and another form is Q. What is the perpetual motion of first kind? There will be no machine which would continuously supply mechanical work without the production of heat transfer as an output, or else the vice versa. That is, it is a system, if there is a Q as an input and W as the output, and such system doesn't exist. That is nothing but a perpetual motion of a first kind. Such fictitious machine is called a PMM1. The heat required or liberated during 1 mass of fuel or substance burned, that is joules per kg Kelvin. It is the amount of heat required for a unit mass burned, heat required or liberated for a unit mass burned for a 1 degree temperature rise. That is nothing but a specific heat. Specific heat of a solid, specific heat of a solid or a liquid is defined as the amount of heat required, heat required or liberated for unit mass of substance bond, unit mass of substance bond for 1 degree temperature rise. That is nothing but a specific heat. Now, the specific heat is, I can say, classified as two things. The first one is specific heat at constant volume. That is CV, C suffix V. Specific heat at constant volume. The definition of specific heat at constant volume is CV is equal to change in specific internal energy to the change in temperature when volume is held constant. It's a new thing now. Small letter represents it is specific internal energy. The capital U represents it is for a total internal energy. This is joules per kg and this is joule. Small letter U, that is specific internal energy, and this capital U represents internal energy. And the definition of specific heat at constant volume is the rate of change of specific internal energy, this is small u, to the temperature when volume is held constant. If I rearrange the term, then I can write du is equal to Cv into dt. If I apply for the two limits 1 to 2, du 1 to 2, Cv dt, this is u2 minus u1, and this is Cv into T2 minus T1. This is the specific internal energy expression I got from this definition. The unit will be joules per kg. Now, with the same thing, if I write it for a total mass, then it will become U2 minus U1, which is equal to mCv T2 minus T1. This is the total internal energy, which is nothing but a joules. That is U2 minus U1 is equal to Cv T2 minus T1. It is specific internal energy. This is total energy for a mass m. Now, what we got a confusion here is internal energy expression can also be written as mCv T2 minus T1. The next specific heat, that is specific heat at constant pressure. The notation is Cp, and it is defined as Cp is equal to change in specific enthalpy to the change in temperature when pressure is held constant. The small h represents a new term for you. This is specific enthalpy, and capital H it is for a total enthalpy. Specific enthalpy unit is joules per kg. Capital enthalpy it is joules. If I rearrange the term here, dH is equal to Cp into dt. If I apply for two limits, dH is equal to 1 to 2 Cp into dt. Now this is H2 minus H1 is equal to Cp into T2 minus T1. This is for specific enthalpy, that is joules per kg. If it is right for a total enthalpy, H2 minus H1 is mCp T2 minus T1. The unit will be joules. Now, what is this enthalpy? Enthalpy is nothing but a heat content in the body. It is nothing but heat content in the body. Or else in another way, mathematically, I can write enthalpy H is equal to, it is the summation of pressure, internal energy. I am writing small letter u because here small letter h I am writing u plus p into small letter v, or else you can write h is equal to u plus p. The unit will be here joules per kg. The left hand side is joules per kg. This also should be joules per kg. This is Newton per meter square. This volume in meter cube per kg. Specific volume because everything is for a unit volume. Now here the unit will be joules. This h is in joules. You also should keep it in joules. Pressure in Newton per meter square and volume in meter cube. This is enthalpy. It is heat content in the body, or else it is the summation of internal energy and product of pressure and volume. The ultimate conclusion you can see here, that is U2 minus U1, it is equal to mCV. Internal energy is always connected to the specific heat at constant volume, T2 minus T1. One more thing you can take here is H2 minus H1 is mCp T2 minus T1. These two expressions are very, very, very important. Therefore, remember this. U2 my change in internal energy, it is mCv T2 minus T1. Change in enthalpy, it is mCp T2 minus T1. Now the next topic is relationship between two specific heats. That is, the two specific heats are Cp and Cv. What is the first law of thermodynamics? That is, Q is equal to Q minus W is equal to U2 minus U1. This is the first law of thermodynamics. Now let us consider a perfect gas. Now consider a perfect gas. Perfect gas being heated at constant pressure. Very important thing. Constant pressure is very important here. From temperature T1 to T2. Then Q becomes, for a constant pressure process, mCp into T2 minus T1. Q is equal to mCp into T2 minus T1. See, when this appears, I will conclude one more thing here. That is, we have a definition, that is Cv is equal to du divided by dt, and Cp is equal to dH divided by dt. When pressure is held constant, when volume is held constant. Now Q can also be written as mCv into T2 minus T1 when volume is held constant. Q can also be written as mCp into T2 minus T1 when pressure is held constant. Now I will take this expression. Now that is Q divided by m into T2 minus T1 is equal to Cv. And from this expression I will write Q divided by m into T2 minus T1, which is equal to C. Now left hand side are equal, then you can tell Cp is equal to Cv. No, so it is not. Therefore, remember this. Whenever you are defining specific heat at constant pressure and specific heat at constant volume, you have to define based on this, not in terms of Q. But these two derivations, these two expressions for a constant volume and constant pressure are true, that we will derive at a later stage. At this stage, specific heat at constant volume is always defined as change of specific internal energy with respect to temperature, and specific heat at constant pressure is always linked with the specific enthalpy. That you remember. Okay. Q is equal to mCp T2. Why I written mCp T2 minus 1? Because of constant pressure. Now U2 minus U1, you know, that is mCv. Always internal energy is linked with Cv, that is T2 minus T2. Now let me apply to the equation number 1. Therefore Q is mCp T2 minus T1 minus W is equal to U2 minus U1 is mCv T2 minus T1. Therefore, work done by the fluid. Now, mCp T2 minus T1 and mCv T2 minus T1. Now, work done can be written as P into V2 minus P1. For which one? For a constant pressure process. Therefore, W is equal to P. For a perfect gas, this perfect gas, P can be written as it is Py is equal to MRT, correct? PV is equal to MRT. Therefore, P1 V1 is equal to MRT1, P2 V2 is equal to MRT2, and pressure P here is P1 is equal to P2. Therefore, this work can be written as W is equal to P2 V2 minus P1 V1. When I multiply here, I will take this. Then P2 V2 it is MR T2 minus P1 V1 is MR T1. Therefore, MR T2 minus T1. Therefore, W is MR T2 minus T1. Therefore, here W. Therefore, equation 1 becomes Q is mCp T2 minus T1 minus W is MR T2 minus T1 is equal to U2 minus T1 is mCv T2 minus T1. That means T2 minus T1 is the common on left hand side and right hand side. M is also common. Therefore, I can write Cp minus R is equal to Cv, or else R is equal to Cp minus Cv. Very important expression. The relationship between two specific heats after considering the constant pressure process, it is R is equal to Cp minus Cv. Very important. R is equal to Cp minus Cv. This is the relationship between two specific heats. For this, R is equal to Cp minus Cv. What I will do, I divide it by Cv on both the sides. If I write this as equation star, Cv on both sides. Now what it will become? R by Cv is equal to Cp minus Cv divided by Cv. R by Cv is equal to Cp by Cv minus Cv by Cv. Then R by Cv is equal to Cp by Cv. This is gamma, I will tell later, minus Cv by Cv is 1. Therefore, Cv I will take it to the right hand side, this I will take it to the left hand side. Therefore, CV is R into gamma minus 1. That means I got CV expression. Now, same star, what I will do, I divide it by CP on both sides. CP on both sides. Now, let us check what we will get here, CP. Now, this is R divided by CP is equal to CP minus CV divided by CP. R divided by Cp is equal to Cp by Cp minus Cv by Cp. R divided by Cp, which is equal to 1 minus 1 by gamma. Therefore, R by Cp is equal to gamma minus 1 by gamma. Therefore, Cp is equal to R gamma divided by gamma minus 1. Therefore, three expressions we got. That is, one is the relationship R is equal to Cp minus Cv, and another one is Cv, that is this one, R divided by gamma minus 1, R divided by gamma minus 1, and one more, it is Cp, it is R gamma R divided by gamma minus 1. Now one more term we got, that is gamma, that is nothing but ratio of specific heat. Gamma is the ratio of specific heat. That is nothing but, gamma is nothing but Cp divided by Cv. Very important. Now Cp I can write gamma Cv. Cp I can write gamma into Cv. Therefore, Cp is gamma Cv. From this I can tell Cp is greater than Cv. Or else from this expression I can tell Cp is equal to R plus Cv. That is R plus Cv. Therefore, Cp is always greater than Cv. That saves one more confusion we can take. This is about the relationship. Let me conclude one more time. Relationship, very important. R is equal to Cp minus Cv, and Cv is R divided by gamma minus 1. Cp here also with the mathematical expression, gamma will multiply gamma minus 1, and gamma it is Cp by Cv, and Cp is always greater than Cv, because from this Cp is equal to this R plus Cv. These are the relationship between Cp and Cv.